network load flow analysis. In the past, we learned how to obtain the voltage solution of distribution network using conventional techniques and non-conventional techniques, and specific to a graphical method approach, which is mainly a non-conventional approach. Now, there are few challenges with unbalanced distribution system and unbalanced DR penetration. Voltage imbalance from uneven DR injection shortens equipment life and reduces efficiency. Now, when you connect any equipment to a three-phase system, which is purely unbalanced, that leads to loss of life or maybe long life, the duration of operation may reduce. Now, the excess neutral current under unbalance risk conductor overheating, because if it is too much of unbalancing, then you will have a natural current which will be reasonably higher, which may lead to neutral current failure. Protection relay may false trip or fail to detect fault in unbalanced conditions. Unbalanced loading increases phase to neutral losses, lowering overall efficiency. Power quality degrades with increased flicker and harmonics from asymmetric DR output. Inverter voltage VR control becomes more complex under phase impedance. Negative sequence currents from unbalanced stress machine and protection equipments. Now, three-phase unbalanced distribution network power flow. Now, we have already learned the single-phase distribution system load flow solution using graphical methods. Now, the same concept, we wish to extend it to a three-phase system now. So instead of a voltage at a particular bus I, now we say VI, VI, and VCI. These three-phase current at a particular node. So what exactly happens? The graph theory and matrix algebra can be used for three-phase unbalanced load flow analysis. Unlike conventional method, no lower upper triangular decomposition of any matrix decomposition is required. Now, there are 5 key matrices, as we discussed in graphical theory, need to be transformed into three-phase studies or three-phase equivalents. All right, such as path impedance PI, path drop PD, loads beyond branch LB, slack bus to other bus drop SBO BD, and load flow matrix LM. So these are the 5 matrices one has to develop for three-phase systems. And the radial network with DG says PV buses. Now the PV breakpoint matrix compute reactive power injection or withdrawal to maintain voltages. Now the 5 key matrices in case of three-phase radial distribution system load flow solution approach, where we'll go one by one, try to understand what is LB, PI, PD, SBO, BD, and LFN. You can perhaps actually refer to some of the articles. As you could see, this has been published in IET by Krishna Murari and myself, and this can be referred. Now first let's start with LB matrix. Right hand side, there are 4 buses, 3 lines. The current moves from actually 1 to 2, 2 to 3, or 2 to 4. And there are extreme end buses are marked as stars. You could see bus number 3 and 4, they are with stars. Red is path from slack bus to bus 3, and green path from the slack bus to bus number 4. Okay, so this is how actually 2 different paths are also defined from the slack bus to the last point. So you have to find the extreme terminal point, and then from slack bus to those extreme point, you can reach through 2 different paths. One is marked as red line, the other is marked as blue line. Now coming back to formulation. So the path from slack bus to bus 4 will be H2 and S equal to 2. That means, let me get into detail here. Matrix identifies the loads beyond branch, identifies all loads beyond a branch in a distribution network where the LB matrix for the distribution network in the given figure of four buses is given by LB, which is SABC bus number 2 multiplied by 0 times 1, SABC 3, SABC 4, and then you can say SABC 2, SABC 3, SABC 4, and finally SABC 2, 3, and 4. Now, we need to understand how this matrix has been generated. Now, it's something like, when you say ones and zeros, they are perfectly a kind of a matrix which decides the graph theory. When you talk about SABC 2 and 3 and 4, so 2, 3, 4 are the buses which are almost of the three phase. And when you say multiplied by 1 or 0, decides the connectivity of those buses to other buses. Now in the LB matrix, each element is submatrix of the order 3 cross 1, except scalars, that is except ones and zeros. Now the moment I say SABC 2 means it is nothing but the three complex powers SA, SB, SC. SABC 3 is nothing but again SA, SB, SC, and 4 means actually SA, SB, SC. So one is going to be the slack bus. There are three different variables, 2, 3, and 4 are the three different buses. But for each bus, I will experience a complex power at bus number 2, at bus number 3, and bus number 4. And at bus number 2, I will have SA2, SB2, SC2. At bus number 3, I will experience SA3, SB3, SC3. At bus number 4, I will experience SA4, SB4, SC4. Now, little bit, again, I'm going back because you know what is SA, SB, SC. So they say that in case of SA ABC2, means this is a matrix basically. So that matrix, if I plot LB, now SABC2 will represent as SABC, three elements will be sitting in the first corner. So one by one element of LB will be a 3 cross 1 size actually. Please try to understand. Similarly, SABC3, similarly SABC4. So they all exist. Now, similarly, when I go to the next one, when I say actually SABC2, 0 means perhaps actually they are not existing anything there. All right. So this is how actually we do calculate. Very interestingly, if you see the paths, what they say, that in case of the second one, if you see, it talks about actually 2 is not existing, 4 is not existing, 3 is existing. In case of third, actually, 2 is not existing, 3 is not existing, 4 is existing. All right. So the second and third layer is defined based on the path. Either when I go from 1 to, that is 2, out of 2, 3, 4, 1 is anyway there, which is common to everyone. Either you take a path 1, 2, 3, or you take a path 1 to 4. That is what signifies from my second and third element. We will learn more in details when we move slowly. Now, similarly, when we determine the path impedance matrix PI, right hand side diagram again very important. You could see there are two buses similar to the previous one, but now we separated out all the three phases. We made it little complicated. So there are three buses at each and every level. Bus number 1, there are 3 buses. Bus number 2, there are 3 buses. Bus number 3, there are 3 buses. And bus number 4, there are 3 buses of a 4-bus system. Bus number 1 is considered to be a slack bus, where we put a huge generator. Now the PI matrix identify all branch impedances in each path from slack bus to end bus. The PI matrix for the distribution network in figure is given by ZABC, all right? That is ZABC1, ZABC2, ZABC3, that is anyway there. But you need to understand that in one case it is 1, 2, other case actually it is 1 and 3. Am I right? Similarly, Similarly, when you move to the ZABC1, ZABC2, ZABC3, there are 3 by 3 matrices representing 3-phase line parameters. Diagonal entities are self-impedances and off-diagonal mutual impedances, very standard, where ZABC can be defined in this form, which is 18.3 as an equation. Now, in the case of 18.2, I like to reiterate the PI matrix that I have obtained when I am moving from actually 1 to 2 to 3 only. If I move from 1 to 2 to 4, then I will have another PI matrix, which is slightly different. Are you getting my point? In case of 18.2, I am moving from actually 1 to 2 to 3. So first row represent 1 to 2, second represent actually 1 to 3. Am I right? But when I can also move from 1 to 2 to 4. So that case, actually, I need to define what is ZABC4 and I have to exist this element. All right. Now, similarly, we can move to path drop PD matrix. The PD matrix evaluates the voltage drop in each branch existing in the path connecting slack bus to the end bus. Again, this is from the slack bus to the end bus. In this matrix, rows represent path under consideration and columns represent a drop in the respective branch connecting slack bus to end bus. Now, what is PD, path drop PD matrix? Which is equal to ZABC, 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 and FCABC is nothing but FCA, FCB, FCC. So Z into FC will give me almost the PD matrix. Okay, please try to understand. So first one is going to be my, 1 and 1. Second will be 2 and 2. Third will be 3 into 3. Second row, 1 into 1. Am I right? ZABC 0 into 0 and 3 into 3. Now, the second one, where actually it has been printed 0, probably that we can consider as a 2 also. Okay, there is a small typo that can be replaced by 2 in the case of the middle term of the second row. Now, moving to slack bus to other bus stops, SBO-BD matrix. The SBO-BD matrix evaluates the total voltage drop between slack bus to other existing buses in each path of the distribution. Am I right? So it is again the same form, but here what we are doing is actually multiplying ZABC1 into FCABC1, and then we are moving to ZABC1 to 2. And the second case, we are moving to, it is basically 3 elements. Am I right? The second will be the summation of 1 and 2, 1 and 2. The third will be again 1, and third term will be 2 plus 3. Okay, so basically when we move from 1 to 2, 1 to 3, 2, 2. Am I right? So first is 1, 1, 2, 1, 2, 3. So this is what actually the 1, 2, 3 path actually being defined actually. So first 1 plus 1 element is fixed for me. Am I right? Then I'm moving to 1 to 2. Next actually 1 to 1 is fixed and the third will be 2 to 3. So this is the structure which has been defined in the graphical theory. So based on those formulas, we need to create those matrices. So all these 5 matrices for any 3-phase network, one has to determine. Now finally, we are coming across load flow matrix, which is LFM. LFM is nothing but U minus SBOPD, where U is given by the voltage of the slack bus, okay, and which is ABC. It could be 111, it could be 000, it could be 0.5, 0.5, 0.5. But it has been symmetrically maintained to create a matrix which is of 2 by 3 size, so that the subtraction will be possible. Now, a search operator is performed on the LFM for selecting the 3-phase non-null vector, any random vector from each column of matrix LFM, leading to the formulation of a new voltage matrix V nu. All right. So, in case of 3-phase unbalanced distribution network, in the presence of DG, I think the problem become now very complicated. Now we have done only simply loads and lines and buses. Now, mathematical models help accurately representing DG behavior in powerful analysis. Proper DG modeling is crucial for assessing its impact on the system. DG models in the power analysis includes constant power factor model, variable reactive power output model, constant voltage model, bus classification based on DG, power output model, PQ nodes, small DG output power, PV nodes, large DG output power. Now, now the problem, again right side diagram, please have a look. The bus number 4 could have actually connected a three-phase generator, distributed generator connected to bus number 4 now. So now once this has been connected, that is at the bus number 4, what we are doing, could you see the right side two subtractions? SA4, SB4, SC4 minus SA4, SB4, SC4. So the first one is basically the load, second one is DG injection. So the difference between load and DG injection will be the the difference between complex power bus number 4. Now this type of DG has real and reactive power at the specified values. The power injection by the DG needs to be reflected in the LV matrix of the distribution network by coinciding, I think, injection. I think considering actually a small typo actually is considering injection by the DG as a negative load, considering basically. All right. For example, consider DG, considering DG injection by the DG as a negative load. Okay. So for example, consider DG, the distribution network in figure, the modified load beyond branch matrix will be LB equal to SAB, 2, 3, 4. But in case of fourth one, it is basically the subtraction in this. So this is basically load. So that is what actually we are doing. Yeah, that's basically. The first is representing your second bus, the third is fine. And in case of fourth, actually it is basically represented by this one. All right. And when fourth case, actually it is the difference between your natural load minus the DG injection. Okay. Now, if I consider it's a PV type DG now. Okay, look at the slowly we are making the problem slightly complicated. There are two digits, one is DG1 and DG2. So there are two digits, PV controlled DG type, DG1 and 2. So consider a three-phase radial distribution network with PV nodes, S1 in figure 1. I think this is figure 18.4 basically. And PV buses treated as generation bus maintain constant real power while adjusting reactive power within set limit to sustained voltages. The net reactive power injection or withdrawal is computed using the PV breakpoint sensitivity matrix. And the next figure 18.5 is the equivalent single line diagram of the system shown in figure 18.4 for PV bus breakpoint injection calculations. So in this slide, whenever you read figure 1 and 2, they are basically figure 18.4 and figure 18.5. So this is the equivalent model of the same network. Now, the breakpoint equation called as PV breakpoint sensitivity matrix, which can be written as equation number 18.8, where you could see the resistance matrix plus J times reactive matrix, which is the impedance, multiplied by the current matrix, which is IABC, will give you the voltage matrix plus the change in delta ABC. The above equation can also be simplified as R matrix plus J times X matrix into your current matrix, which is equivalent to P plus delta. So this is a very 18.9 become a simple equation of R plus Jx times I minus delta IABC, okay, equal to delta voltage, that is change in voltage plus delta del ABC. Now this model further can be extended that you can also rewrite this equation as X matrix all right, and R matrix uh, multiplied by I matrix, which will give you the voltage matrix. So I have combined as a single matrix Rx multiplied by the current matrix will give me the voltage matrix and delta matrix. So with the assumption of all voltages being close to 1 per unit and the phase angles are small, the following equation can further be simplified. The changes will be, there is not existing. So 18.11 and 18.12 can be extended out of 18.12, considering the voltages become close to 1. Again, if I combine 18.11, 18.12, 18.10, the equation will look like a complicated X and R equations, delta Q, delta P, delta V, delta delta. Now I'm landing to 18.14, which says XR minus RX delta P delta Q equal to delta V delta P. This equation we have already derived in a similar form, in the previous lecture also. Okay, the same equation we have already derived, but this is for a three-phase equation where the X and R of delta Q, delta P, delta V, delta delta are all of three-phase systems. And in the meantime, delta ABC is, basically it's a 0, 0, 0 matrix, and delta P ABC is also null matrices. Okay, and delta V ABC are given by the following equations. Now, using the above substitution, the sensitivity matrix can be reduced to now 18.15, which simply talks about X times delta Q will be equal to my delta V, right? So the exact amount of injection or withdrawal of reactive power to or from the PV buses needs to be reflected in the LB matrix of the network. If the computed reactive power infringes on the boundary constraint, then reactive power generated / withdrawal will be positioned or fixed at the violated boundary limit, and the DG will behave as a PQ generator. Remaining matrix will reset or reconfigure themselves in accordance with the changes in the LB matrix. Therefore, the proposed algorithm is capable of handling various, and the modified LB matrix is now can be considered LB equal to the same matrix. But what we have done actually, we are now subtracting that SABC PV B1 matrix in case of both 3 as well as 4. So the new LB matrix will look like for a distribution system with a PVB number of PV buses. So these are the number of PV buses. Something, okay, it is some other message. The sensitivity matrix or breakpoint matrix is formulated using the steps given below, where X is nothing but X matrix that you create 18.17. The diagonal entry XKK ABC equals to the sum of the positive sequence reactance of all three-phase branches from the substation root to the PV node. In our case, it is either 3 or 4. Off-diagonal elements, that is XKL ABC equal to XLK ABC. No shared path, that is XKL ABC equal to 0. If there is a shared path, then XKL ABC is the modulus of sum of the reactance of the common section. What I mean to say that, for example, path 1, 2, which is common to 3 as well as common to 4, our path 2, 3 and 2, 4, they are actually independent. They are not common to anybody. Now, hence we can calculate the sensitivity matrix where X delta Q equal to delta V, where delta Q is given by the matrix, as you could see, and delta V is given by this equation, 18.18, and delta delta equal to 0 and delta P equal to 0. So this is my final equation for sensitivity matrix. Now, finally, I can just explain you the whole flow, how we are going to write an algorithm if required. So first, load system data, and then calculate LB and PI, create three-phase voltage matrix V, set tolerance value, which is 0.001, set number of iterations, let's say it is 100. Then you calculate what is FC, FD, SPO, BD, calculate matrix V new as per the algorithm, determine the convergence between V and V minus V, and if the convergence is equal to minimum value from the convergence matrix, then you can simply solution converges. If no, then you update the old value by a new value. And if the iteration number is less than 100, repeat. If it is more than 100, you exit. So this is what actually the conventional algorithm is altogether. Now, we will get into a small case study and try to understand how it is working for three-phase systems, because three-phase load flows are not very, very common. Normally, we limit ourselves to single-phase load flow solutions only. But I'll be very happy actually if some of you can extend your work to three-phase distribution system. In case of even smart grid, we consider it is a single-phase system. But why not it's a three-phase system? Because it is unbalanced, because we know very well it cannot be treated as single phase. The moment you make it three phase, there could be a number of challenges that one can foresee. The moment you introduce unbalance in the systems. To evaluate the performance of the proposed load flow algorithm in the presence of distributed generators across various standard distribution systems, so there are two systems we have considered, IEEE 13 bus, IEEE 123 bus. The 123 was purely radial and 13 bus was weakly meshed, includes unbalanced loads and laterals. And in case of 123 bus system, it is large feeder with mixed overhead / underground lines. Now IEEE 13 DG at bus 633, IEEE 123 DG at bus 19. So every DG is treated as a PV node with fixed voltage magnitude of 1 per unit. Case study, modified IEEE 13 bus distribution network. So as you could see that this is the 13 bus network, but it has been slightly modified. Now DG is able to maintain the voltage magnitude at bus 633 equal to 1 per unit. DG is integrated as 633 bus. We have integrated the DG, which was not there in the original system, but we assume there is a DG, okay? And DG is treated as a PV node with fixed voltage magnitude of 1 per unit. Now, when you get into scalability analysis is carried out, because this is a graphical thing and three-phase matrices, whether it is capable of taking to a larger node or larger bus system is a question. So scalability analysis is carried out because, you know, 4-bus system, we are very comfortable, you know, we can look at it and create our matrices. But when I go for 100 bus, 200 bus, whether it is working or not. So scalability analysis is carried out with 123 bus test system. A system size grows up to 123. Graphical method, computational time scales more favorable and convergence time remain almost constant. Means what they are arguing, if it is a three-phase system, in case of classical technique, it is a huge challenge. Even forward, backward, if you recall, what we have to do, you have to assume this is 111. Then you calculate, the load current and then the line current, and then you come back and then you calculate the voltages. So every time you have to go in three-phase way, you know, so the voltages are not same. So convergence in a three-phase system in 123 is very, very challenging. So probably here this claim that actually this is quite good, then moderate DG injection up to 8 per unit of feeder load, raises voltage downstream, improving minimum voltage margins. Excessive DG above 1.2 per unit can cause overvoltage at upstream nodes unless reactive power is properly curtailed. So as you could see that R plus Jx convergence speed, if I keep on increasing the value of R, please all of you have a look, right side diagram is very interesting. So R by X ratio we say for distribution system is high, but if it is keep on increasing, we know for neutron absolute phase, but in this algorithm, we intentionally increase the R by X ratio starting from 1 to 1.5 to 2 to 2.5 up to 5. That is the worst one can ever imagine, 5R plus Jx. But even though the convergence actually doing a good job. So the 13 convergence time, if you see, it is just 0.01, graphical method 0.01 second, and 123 bus also 0.01 second. Means just one click you get the answer. No time. All right. So this is the strength of this logic. Once all the matrices created in one click, you get your answer. So what is the reason for such a fast convergence for graphical method? Why do we go for such kind of methods? This algorithm utilizes simple matrix operation to solve the LF problem of the distribution network. Multiplying matrices, adding matrices, subtracting matrices doesn't take much time really. All right. The formulation of PI matrix ensure a minimum number of search operations to identify all paths connecting the slack bus to end buses in the distribution network. Also, this matrix provides information regarding the branches existing in each path in minimum such time. This algorithm is formulated entirely on various matrices, formulation and computation, even at the stage of upgrading the voltage at every individual bus. With this, actually, we are coming to an end. It seems to be, again, very simple, but honestly, very exciting. But only when you take a small numerical problem. Probably I could have solved a numerical example to make your life very easy. Means I could have taken a 4-bus system and given you numeric values of R plus Jx and everything, and then created those matrices, and then obtain a voltage solution could have been a better choice. But I will strongly recommend to refer the Krishna Murari's article in IET, which really talks about very much in detail. So all the student I request if you refer, because that whole article we squeezed to a 30 minutes presentation. So if you go through that article, it is very well written, very much detailed presentation was there. So I request everyone to experiment at least a small 4-bus system voltage solution, 3-phase with DG. So first 3-phase system voltage solution, then 3-phase system with DG, and then 3-phase system with PV, multiple PVs. So these 3 case studies, hope you can solve and yeah, please.
So if we further reduce the convergence time, then will it be a good decision for work to users?
How to reduce the time further, you are saying?
If we further reduce this by some algorithm or other, but will it be worth?
Oh, why not? Why not? But you need, for that actually you need to have altogether a innovation idea, isn't it? And I mean, it's always excellent. There is no end to these stories, you can still continue saying. For that, actually, you need to identify where conventional methods and graphical methods fail or face challenges, and then try to address those. And in that process, you will come out a way. And then you have to check the time, solution time. And then if it is reasonably good solution time, then it is worth doing it. That is how the research normally progresses. So you have to now find what are the limitations of this problem, or you make your problem complicated in a way that this fails. Am I right? And then you try to address and also assure to the consumers that this is also reasonable, then it's a good research. Am I right? Because time will be the last one. First is the uniqueness. What is the extra thing you are bringing to the top? Okay, good. So we'll consider a few example of load flow solution in OpenDesk platform. So because being a practical person, let us not only discuss but also try to solve now. So I request that OpenDSS is a platform which is open source. Am I right? How many of you have used OpenDSS? If not, please use it. You can solve any load flow solutions very easily for any network. Okay. We will get into. So I'm indirectly teaching you a tool basically how to use OpenDSS for your day-to-day load flow analysis. Introduction to IEEE 13-bus distribution system. This feeder is very small and yet displays some very interesting characteristics. Short and relatively high loaded for a 4.16 kV feeder. One substation voltage regulator consisting of 3 single phase units connected in Y, shunt capacitor banks, inline transformers, unbalanced spot and distributed loads. Now, if you see one line diagram of 13 bus system where there are transformers between bus number 633 and 634, 630S, rating 115 kV versus 4.26 kV. So there is one transformer, and then you have a AVR, voltage regulator, in the top, as you could see, and these are the loads. And it's a very classical system, all of us used in the past. Now, how do I use the load flow solution of 13 bus using OpenDSS? Because many times, for me, making a load flow algorithm is not research, and that is not interest to me, isn't it? But I need voltage solutions. So that case, I will strongly recommend, instead of writing your own algorithm or creating innovation, you perhaps use OpenDSS, which can quickly give you voltage solution that can be used for your further application. The advantage of OpenDSS, it is very much compatible with any format of platforms that you use. It could be MATLAB, could be C, could be C++, anything that you use. OpenDSS can accommodate those output data. So first of all, global setting and circuit creation. You have to create the network as you wish. To clear, set default base frequency 50, new circuit IEEE 30 node circuit, and base kV 115 per unit, and then angles, and then finally substation transformer data, new transformer data. You can enter all the data. Then default base frequency, you can consider 50, and the system can also be considered 60. And the new circuit that initiate is three-phase circuit, IEEE 13 node circuit with a 115 kV stiff source at source bus, the large MVA and shifting approximation at infinite bus, and an advance angle of 30. So this is basically your system description actually. And uses inline RPN mass, that is 8 upon 1000, that is 0.008 ohms, to make the transformer modeling basically. Okay, so when you see the system description, the first case, the way it has been defined. The second case, the transformer, two bindings, of 115 kV versus delta type 4.16 kV, Y type, delta Y type, okay. So by defining the yellow strips, you are defining the circuit as well as the transformers of the system. The code for another transformer can be followed similarly as above. Your network may have actually more than one transformers, okay? So then again, you have to define clockwise again and again. Now, third, we move to mid feeder voltage regulators. You may be having some voltage regulators in the network that need to be defined. Load definitions, loads need to be defined. Capacitor definitions, capacitor banks need to be defined. So, three single phase low impedance transformers emulate the regulators, which is in the top that you have seen as voltage regulator. So that has been modeled, and then defines each node's load in kilowatt or kVAR. And finally, the shunt capacitor, whether it is reactive power, rating, everything has been defined. So once you define all these terms, then you have to go for line now. So line parameter, where you have to say what is the line and line segment. Each new line command connect two buses using predefined line codes and lengths to build the IEEE 13 feeder layout. Okay, the distance, the resistance, everything has to be defined. And then you have to go for some switch definitions. Three-phase switch between buses. There was a switch also. Could you see that in the previous diagram, 13 bus? You could see 71 and 692, there is a switch. So you could see there is a kind of a regulator, the voltage transformer. Then you have a switch, line, load, everything can be easily defined. And then voltage of each bus, set voltage buses. There are three types of buses where 115, 4.16, 48. Okay, aligns per unit base values of different voltage levels, and then compute the actual line length in per unit. Then finally, you reach to the solve point. Solve. So voltage Ln nodes, so current Lm, so power kVLm, so losses, so taps. Displays voltage, current, element power losses, and regulator taps to the DSS console. So everything you can download it. All right. So this is how actually it is expected. Tell me.
Some questions.
Please. Please tell me, sir, if make a no. Please go ahead. Yeah. For islanded, what is the question?
If make a islanded microgrid, then it is necessary to check the load flow. The microgrid generation is 40 kilowatt, solar plus wind.
I mean, you see, the question is whether I need to go for a load flow solution of a islanded microgrid which has 40 kilowatt of solar and wind. Now, first actually we need to understand what we are looking for. If you are looking for a voltage solution in an islanded microgrid, yes, you can do that. And wind and solar is fine to me. It's not an issue. So you can solve load flow for a small microgrid means it is a small distribution system, but which is islanded. There is no super node or a bus or a grid is there. Okay, I think still it is possible. Still it is possible. Yes. Okay. So voltage solution is nothing to do with whether it is islanded or grid connected. You have to again assume a bus as a PV bus because that islanded microgrid will have some generating sources. Okay. So that will be your slack bus and we can proceed. And this is the simulation result. So this losses report table shows for each network element, the real power kilowatt and reactive power kVAR losses in the salt bar flow, plus each element share of total delivered power. At the bottom, it seems up line losses, transformer losses, and total losses. Compares that to the total load demand, which is 3454.7 kilowatt, giving an overall loss percentage of 3%. And you could see that everything is now clear. You have losses in each and every segment and total losses, loss report, like someone is interested to know how much the system experienced the losses and how each and every component contribute to the losses. That also one can calculate, even the transformer loss, even the line loss, even the load loss. Okay, so this is just a case study, it's open platform, but you need to sit and work a couple of nights, then only you'll be able to get those results, but it's not impossible. That's what I wanted to highlight. So it's very simple. And now we can go to circuit element currents. Someone is interested to know the current and angle. So element currents for each power delivery element, example source, transformer, regulator. The report lists per phase current magnitude in A and phase angle in degrees, showing exactly how much current each device is carrying from its connecting bus. Okay, current flow to each and every devices can be calculated. It also breaks each component into real and imaginary part. So you can see both active and reactive current contribution flowing to each element of the system. Okay. So this is another set of data because the data is what we are showing is not typed data. They are the simulated data. So we simulated and we are just showing for your benefit so that when you run the program, you will experience exactly the same thing. Okay, so now what has happened, you understood everything. And then you have a masterpiece to validate if you, as you mentioned, if you like to experiment some new things, you should have a reference so that you are not diverting from what exactly desired to be. So my recommendation, because in our time we used to write coding to get voltage solutions, but I don't recommend anymore. If there are open sources available for conventional approaches, please use that. All right. However, for any new innovation that you like to carry out, that you have to do your own way and resolve it. And then power flow. Loss, current, how you are determining the power flow. This is a very, very important thing, especially in smart grid application. The power flow between each and every component is very, very important. So the circuit element power flow table shows for each delivery element, source, transformer, regulator, per phase real and reactive power, how many kilowatt real and kVA reactive are flowing into the element on each phase from the named buses. Apparent power and power factor, the resulting kVA and power factor for each phase, plus a terminal total that sums all phases. So you can see the elements overall loading and power factor. Now then you can get into voltages. The final one is the voltage solution, am I right? This table reports for each bus and phases line to ground voltages and line to line voltages of each and every one. So you could see the currents, losses, power flows, and voltage solutions. Right? This is also very, very important for any smart grid applications. Now we can have one more case study where management of energy storage dispatch in unbalanced distribution network using OpenDSS. This is another case study. You have a battery in your smart grid, and you like to know how those energy storage dispatch happening in case of a unbalanced, because the battery is three phase to me now. Okay, battery is also three phase. Network OpenDSS. Now see what we are doing here. Now optimization and load flow techniques are required to determine the optimal size and dispatch of ESS in the distribution network. Right. So whatever you do, first of all, you need to know what is the size and where it is to be located. The optimal energy management scheme of storage directly impact the benefit of the system besides size. A significant study is done based on the DS dispatch in a practical low voltage distribution network, because this is a unique case study where you all have interest. In a smart grid, I want to see how my battery is behaving, charging, discharging cycle in case of a three-phase distribution network. But I hope you are very sure that the battery could be of a three-phase battery, am I right? Similar to a load. The battery also can inject power to a three-phase system. All right. So the distribution system is, today we are doing it for single phase in the lab. You can do it for three-phase if required. That is the reality. A significant study, the distribution system is integrated with PV and storage. The uncontrolled storage operation leads to losses to the operator, and frequent charging, discharging will lead to battery degradation. The present work describes method to dispatch DS system in a practical Indian distribution network using OpenDSS and MATLAB. So one can do it with MATLAB, one can do with OpenDSS, depending upon how you like to evolve. So a central storage controller is used to control the storage fleet using different dispatch nodes. So this is where what we are doing is, in case of the changes and challenges in modern power systems. First is actually we talked about voltage and frequency fluctuations, increasing demand, penetration is going to be completely intermittent, and non-coincidence peak that you have already experienced, and reverse power flow. So these are the main challenges we see in case of a uh, distribution system, and especially when renewable generation is more than load, the situation becomes worst. And how do we do that? We need to have some storage device to accommodate those energies. So to that, actually, we thought of giving you an explanation of IIT Roorkee distribution network, and we'll explain actually how this has been simulated. So the single line diagram of IIT Roorkee system, because many times I talked about IIT Roorkee system, but today I'm giving you the complete single line diagram, which has already been shown in the past. But this single line diagram actually we have developed, means our student team actually have developed over a period of time. You can develop the similar kind of system for any academic campuses. And fortunately, this system, what you see, is one of the very, very almost exact what the system is. Line parameters also is for the standard data. And we determined that, a couple of points we can put some batteries, their energy rating and power ratings are being determined. But we do not know how do they behave when they are in practical study. If I put them on ground, I must know actually how they are going to behave. So time series simulation for PV output and loads due to their variability and uncertainty. Detailed LV modeling as well as inclusion of multiple features. Three-phase load modeling, which is an important aspect. So if I would have taken IIT Roorkee system and carried out single-phase load flow, probably we would not have produced any IEEE transactions. Okay. So when we made it a three-phase load flow, people appreciated. Then we have gone for a practical case study, people further appreciated. So I need not depend on IEEE 13 or 123 anymore. I have my system. But once I do this, I also apply to IEEE 13 bus of 123 system just to say that my model is working. So then people will start appreciating your own models, right? So probably who knows actually some part of North America, people may be using our model and we are using their models. Am I right? Possible. Very sure about it. So this is how actually load and PV modeling is being carried out. So the loads are modeled as constant P and constant Q load models, divided into three categories: hostels, residential, and apartments. Load shapes are defined in all forms, that is summer, spring, and autumn. And we try to simulate a total of 1.8 megawatt rooftop solar, because there is an interesting story. When we started working this problem, we had only 1.8 megawatt of PV. After that, we put another 1 megawatt. It became 2.8. So when we have carried out the case study site visit by students and staffs, that time the true simulation was carried on with 1.8 megawatt PV. So this case study is because of which it was for 1.8 megawatt. So the PV system element of OpenDSS is used with combines, which combines both PV array and inverters. We are just helping you in the second block. The PV system, okay, element of OpenDSS is used, which combines both PV array and inverter modeling. So instead of modeling separately inverter and PV models, we have taken PV system where complete PV system is available to us. So using that, actually, we have modeled our IIT Roorkee distribution system. And then move to the storage element modeling, where the status of initial and final energy over a period of 24 hours are being modeled. And then peak, shape, follow, time, schedule, load shape, and peak shape low are being actually defined. What is peak shape? In this discharging mode, the storage attempts to keep the power in the monitored element within a specified bandwidth of a off or low or off or below a kilowatt value. Follow is a term for a battery. It operates the same as the peak set mode, but the control is triggered by time. Okay, will I read again what is peak save for your benefit? In this discharging mode, when the battery is discharging, the storage attempt to keep the power in the monitored element within a specified bandwidth of or below the kilowatt value rating. Okay, and then time, in this mode, the storage operation is triggered by time. The storage charges or discharges according to the remaining energy capacity. Schedule. In this discharging mode, a trapezoidal shaped dispatch schedule is followed by the storage. Right? Load shape, both charging and discharging of storage follow as per unit load shape curve. Peak, save, low. Charging mode, where the storage devices will set to charge when the power of monitored element drops below a specified target. Now, slowly we get into the techniques description. Here, one interesting thing I like to disclose, that we have actually used rigorously the OpenDSS, but not as an independent tool. We used actually MATLAB as a base, and MATLAB used to call DSS as and when required. Am I right? And similarly, the MATLAB again get connected to OpenRT as and when required. Are you getting my point? So there's a lot of history, I do not want to make you nervous by saying all these things, but now let us understand that the MATLAB and OpenDSS can be connected or integrated. I'm very confident at least half of you will be able to take advantage of this exposure and opportunity and do something great in your own field. So what we are seeing, the MATLAB which is the DSS and MATLAB, they are combined. Open DSS driver result analyzer, and your minimum loss and voltage deviation we calculate, and fix the charging and discharging mode of storage, calculate system losses and voltage magnitude, set storage limit, and uh, you know life cycle analysis, change the dispatch mode, operate storage controller, input system parameters, PBN storage rating and parameters, time series simulation, three-phase path flow solver. So what I wanted to say, the blue one is coming from one server, and the brown one is coming from another server, and one is helping the other one. And the very interesting part, you see from the blue block to we are jumping into brown block where the data is being fed. And once the simulation carried out in the top layer, they again go to the blue blocks. Okay, so there is a extreme serious link, which you have two different tools. This solves and provide you data here. This fellow does and provide data here, and they work actually in coexistence. Okay, so this is how actually MATLAB and OpenDSS work actually in a system. So this distribution system data such as load profile, PV and storage rating are collected. The storage controller parameters are updated with the element list to be controlled, the reserve and the initial state of charge. The MATLAB COM interface is initiated and the base case and PV penetrated network. The storage is integrated with the selected parameter and operational limits. The results for various dispatch modes are analyzed for both charging and discharging. A comparative study is carried out between various dispatch modes, and the one with minimum losses and voltage deviation is selected for dispatch. Now, interfacing MATLAB with OpenDSS, the simple workflow, the right hand side I've given you, but how do you integrate those two things? Okay, start and compile. In MATLAB, launch the OpenDSS COM server and compile your main.dss file to load the circuit. Set dispatch mode, that is from MATLAB, send a single line command, set storage control mode equal to 1 to switch how your battery or storage behaves. Runtime series power flow, where tell OpenDSS to run 24-hour solvers, mode daily, number 22 solved. So you sweep through a full day of operation. Because battery, until unless you work for 24 hours, there is no fun, okay? And then pull back results and compare. Read total losses and bus voltage right into MATLAB, circuit.losses, and all bus V mag per unit. Store them, then loop over each mode to pick the one with lowest losses and smallest voltage solution. So it is a classical way of doing it, but the idea is actually how my OpenDSS and MATLAB they are integrated. Okay. And these are a couple of simulation results as you could see, and the battery with 90% DOD and 80% DOD degradations, lifetimes 5 years, 7 years. But I'm very lucky, all my simulations says the battery can run maximum 5 to 7 years. We cross 7 years now. Still it is working. Yeah? That's good. I should not say that. And you could see the number of cycles, how the battery with respect to DOD value and energy stored in battery with charging and discharging power, all these solutions with PV base case have been demonstrated. Total active and reactive power losses over 24-hour period. And then losses comparison for base case storage with or without controller and PV integration. This is another set of simulation results where voltage at various nodes with seasonal variation and voltage with various nodes for different modes of operation of ESS. Okay, so you could see how the ESS behaves and how the PV behaves. The charge and discharge modes are identified for minimizing the system losses. The battery can charge and discharge in any way, but the idea was to actually optimize the cycle and also see to that the minimum loss will take place in the system. So that was the objective function, to reduce the system losses. Okay. I think this is how actually we have come to an end today. I think to be very honest, actually, this almost today is one PhD work. What we have learned is almost a full PhD of 4 years. But I thought of sharing all these wonderful experiences because I still remember OpenDSS and MATLAB integration itself took actually months for students sometimes, struggling and then working very hard and finally running it, and then they jump with joy saying that, oh, this is working now, very good. And please type if you have any questions. Yeah. I think with this we come to an end. So my suggestion to you, I will strongly recommend you to read Tripti Gangwar, NP Party. You can read articles for the second part of OpenDSS and MATLAB combination simulation with battery storages. And you can read the article of actually Krishna Murari and NP Party for the graphical method, single phase and three phase load flow algorithms. So I think these two researchers' work, if you follow probably yesterday's and today's lecture, you will be able to understand. Not only understand, but you will also start appreciating. All right. So and this is, I mean, sometimes it looks to me that this FDB course is just listen and talk, but it is not so. Each and every class has a research impact, very serious research impact, and most of the things actually we might not have really learned or studied, and but it's eye opener where you could see, oh, a lot many things can be done. Am I right? And once you start enjoying with first of all, microgrid is our base. Today we talked about, for example, PV integration. We talked about multiple DG integration. We talked about battery integration. Then we talked about conventional and non-conventional load flow solutions. Then we talked about how a tool can be used. Then we talked about how the tool can be called by my MATLAB, what I normally do. So it's a whole package of opportunities before you. Now you decide what you want, and now you decide actually where you like to go. All right. So this is the basics one must grow. Once you have these basic tools, probably you don't know at what given point of time, what application, what work actually one can use. Right. So thank you very much and appreciate for your patient hearing.
Any questions, please? Okay, well then we close today's session over here. Tomorrow. Tomorrow class same time.
Tomorrow?
Saturday. We will have class tomorrow.
Yeah. Yes.
Okay. So tomorrow we will have class at 5 p.m. as per the schedule. So thank you very much. Thank you, sir.